Mr. Baina here, and welcome to Concept Map Lessons. Today's episode we'll be talking about projectile motion. What is a projectile motion? What are the different principles of projectile motion that we encounter in our day-to-day lives? If you throw an object into the air, it will produce a projectile motion. A projectile motion is produced of a moving object in air, producing the two component motions, and these are the horizontal component and the vertical component. This vertical component of that moving object in air is always acted by what we call the force of gravity. Let us consider the motion of the object and its two different components, the vertical and the horizontal component of this projectile motion. First of all, the path that the object is traveling into that creates the parabolic motion is called the trajectory, or the trajectory of the projectile motion. So let's start. The projectile component of the cannonball has both the x and y components. As the velocity of the y component reaches the topmost of the motion, it becomes zero, while the x component is always constant until the ball or that cannonball lands into the ground, as it goes back to the ground because it is always acted by that gravitational force. Objects thrown in air requires the best launching angle to maximize its projectile motion, and this is equivalent to 45 degrees. 45 degrees is a special type of angle for a projectile motion because these allow the object in air for a longer time to travel and will produce the longest range of the component of a projectile motion. Observe the animation illustrated here, and you see that the highest range and the longest time the projectile motion can travel into air is that 45 degrees. An example to projectile motions are the following: the speeding bullet. Again, this is the trajectory of the projectile motion. As the bullet is fired from the gun, it actually moves in a horizontal direction, but since the bullet is also acted by the gravitational pull, it is as if the bullet is just dropping into the air going to the ground. But since the bullet is traveling so fast, you cannot notice this, but the same thing happens to a bullet when it travels in a horizontal direction, and that is following again the action of gravity in the vertical position until it reaches the ground, and so it travels in a long range, as we call it. Another example of a projectile motion is the volleyball. The volleyball is one example that you see more often the projectile motion or the trajectory of a projectile motion. The trajectory resembles a parabolic path. Now let's talk about the most important key elements in a projectile motion. First of all, we will talk about the maximum height that a projectile motion can reach. We're talking of the vertical component in here, or the y component of the projectile motion. The maximum height of a projectile motion is reached when the vertical velocity will also reach to zero. So this is an example of a projectile motion. This is the trajectory or the path wherein the object is moving. So these are the screenshots of the different positions of our object at a very different time interval, and you see that the y component, or the velocity along the y component, is very high from the initial position, but somehow it reaches that position wherein the velocity along the y component becomes zero because of the action of gravity that balances out the velocity or the force of the escaping velocity. Now, as the component of that object reverses its position, it goes back to Earth, and since these two positions of that object is of the same level, whatever the velocity here is the same velocity that it reaches also into this level. So basically the same level will have the same velocity, and if the velocity in here is very high, naturally the velocity also of this one is also equivalent to this velocity. And this is the danger of what we call the stray bullet, because when one shoots a gun or fire a gun during Christmas or New Year, the same velocity of the bullet flies off into the air, but when it comes back it will have the same velocity as the escaping velocity of the gun that is produced when it was fired. So it is the killing velocity, and it reaches into the same level. If somebody is standing in there, it will also have the same effective killing velocity. So that's the danger of understanding the that's how we understand the stray bullet of the science of projectile motion, that is also applied to the case of a stray bullet. And so we have the formula for the maximum height of the projectile motion in terms of the height y component, and y component from the ground is equal to the initial y component, as if the object is thrown by somebody. So from the ground we have the height also of the person that is throwing the object, so there is an additional component of y sub o. So if y sub o is not present, then we can consider this as a zero value that will be added to the velocity of the initial y component, multiplied it by the time, so the second can be cancelled out, and so we will remain a unit of meter or meters plus 1/2 the gravity times the time square. So this is how you compute for the different component of the traveling vertical component of our projectile motion. And of course we have another formula. If we consider also the velocity of our vertical component, then we will be following the formula. The velocity of the final velocity along the y is raised to the power of 2 is also equal to the square also of the initial velocity of the y plus twice the gravity multiplied by the change of y, or just the y, the distance of y. So we will apply these formulas into the next slide. So here we have a problem. This is a stone that is thrown upward. This is the trajectory of the path of the motion of the stone with a speed of initially 20 meters per second, and it is caught somewhere in the 5-meter height distance from the same level where the stone is thrown. So the question is, how fast was it going when it was caught? So now we are going to compute for the time of the catching of the object when it was caught in here, and letter B, how long did the trip take? So basically we are going to calculate the speed when it was caught and the time when it was caught. So how long did the trip take, for example, from here 20 meters only up to 5 meters? So we will check that out. So if you recall, I am going to give the all the given in here. So we have the initial velocity of the projectile motion, which is 20 meters per second, and the height that is already given, that is 5 meters. All right, and then also this is also given, but this is obviously standard. The average acceleration due to gravity is 9.81 meters per second squared, or sometimes they just write 9.8. But for the solution of this problem, and so the solution is how fast was it going when it was caught. Now we have the formula: the square of the velocity, or the final velocity along the y-axis, is equal to the square of the initial velocity, which is 20 meters per second, plus twice the gravity, which is negative 9.81 meters per second. Why it is 9.81? Because it is going back. All right, so the gravity is going back. We have a negative direction, so we will be using negative 9.81 meters per square of a second, multiplied by the height of our y, which is 5 meters where it was caught, and then so the final velocity in here where the object was caught at 5 meters high is equal to 302 meters square per second square. And so this is raised to the power of 2. We convert that into the other side, that will become square root, and we will be able to find the actual velocity that it was caught. So definitely this is 20 meters per second when it was initially thrown. Naturally this is already in the higher elevation, so definitely I would expect that it should be lesser than the value of 20 meters per second. So let's check that out. And so again, this final value of our velocity where the object was caught is 302 meters square per second square, and we'll transfer the power 2 to the other side. That becomes a square root, and so that is plus or minus 302 meters square per second square, and the value is negative 17 meters per second. That should be the velocity. All right, why negative? Because it is moving in the opposite direction now, so it's going back from the zero velocity here, so it's going back to Earth. So we will also, because this is a vector quantity and we are very serious about the direction, so we'll consider the negative 17 meters per second. So that's the answer to letter A. Now let's proceed to letter B. How long did the trip take? And so actually when we talk about how long did the trip take, this is not from the value of 20 meters going up, then it's going to end at the zero, then there's another time to from the zero velocity to its velocity where it was caught. It's just simply the time from 20 meters only up to the time where it was caught. So this is the 5 meter. So within the 5 meter we have the formula. So our solution for this is we'll make use of the formula for gravity, or I'm sorry, for the acceleration. Acceleration is actually equal to the velocity of the final velocity rather minus the initial velocity over time. That should be the acceleration. But since we are going to make use of g, because this is a vertical acceleration, that's basically the gravitational pull, and so that is standard, and we will calculate for the time, because it is the question is how long. So the time will be isolated, and we'll change the gravity in here. We'll transfer the gravity as a rule of the calculation or transposition of the formula, and so we'll be able to calculate now, which is the final velocity along the y minus the initial velocity along the y divided by the gravitational acceleration. And so t is equal to negative 17.4, which is going down, and also negative 20 meters per second, which is supposed to be also going down, because obviously this is the formula, that's negative 20, which is the initial velocity, and divided by the 9.81 meters per second square, and so the time is equal to 3.8 seconds. So from 20 going to 5 meters, that is basically 3.8 seconds. And so another important key element in the projectile motion is the range. So basically range is the horizontal displacement from where the object was thrown. So here's how we are going to compute for the range, but we have to understand what range is. So the range basically is the displacement in the horizontal direction. And the different comparison by the different angle is that when your angle is 75 degrees, you are going to have the shortest range, and if you are into the 60 degrees, you will have a longer range, or 30 degrees similar to 60 degrees, the same range. But as I have said, the special angle is 45 degrees, and so if you want to maximize the range or to increase the height of the range and allow the object to travel a little longer in the air, so you will make use of the special angle for a projectile motion, and that is 45 degrees. And the formula for range is actually in terms of the velocity along the x-axis, which is always equal to the velocity along the initial velocity along the x-axis, because there is no hindrance to the velocity along the horizontal component, unlike the vertical component, which is always acted by the gravity. That is why as the object in the vertical component is thrown upward, it slowly is going to decrease until it reaches the zero velocity and it drops back to earth. While the range is actually calculated as the x, or the change in x, or the displacement in x is equal to the initial velocity where the object was actually thrown into the air. So the component of that initial velocity along the x multiplied only by the time, that should be the range value. And so the next slide, we will be making use of this formula to calculate for the range. And so problem 2, here we have the component of the projectile motion. The original velocity actually of the projectile motion is given by this basically a vector quantity component method. And so we have the y component VOY, but that is not our concern for now. So our initial velocity along the x is actually equal to 25 meters per second, but the range actually from the initial velocity when the object was thrown at the initial velocity along the x at 25 meters per second will produce a range of equal to 15 meters. And in the problem is that what is the time required for an object to reach the range of 15 meters if the initial velocity is 25 meters per second, obviously. So now we are going actually to calculate only for the time for this object to reach the range of 15 meters. And remember that the formula for our range, or the displacement, which is 15 meters, is equal to the initial velocity, which is 25 meters per second, multiplied by the time, because this is what we are going to calculate now. And so the solution is, and now the solution again is to simply isolate our time. So we are actually going to look for the time, and so we are going also to change the formula, and our formula now is the initial velocity along x and divided by our range, which is the displacement x, and the time is, now we are going to replace the value with 25 meters per second divided by 15 meters, and so the answer will be 1.66 seconds. So it only requires 1.66 seconds for the horizontal velocity to reach a range of 15 meters. And so the last key element that we are going to talk about in a projectile motion is actually the symmetry. So what is symmetry? So symmetry is actually the parabolic shape of the projectile. But remember, there is also an element called non-symmetrical projectile motion or projectile path, trajectory. So I have here two types of illustration of a projectile motion. One is a symmetrical projectile motion, and the other one is non-symmetrical or asymmetrical projectile motion. And so when we speak of a symmetrical projectile motion, this is the perfect parabolic trajectory of a projectile motion, wherein this part in here is symmetrical to the other part or the other side. So the dividing line is actually where the final velocity from the initial velocity will reach to zero, and this becomes the initial velocity and this becomes the final velocity if you are going to calculate your projectile in this section. And so here is one example. For example, this is a cliff or a building wherein you throw an object in a projectile motion, but since it is elevated already initially, and so the object can still continue to drop to the ground into that specific height. And this is also an example of a non-symmetrical motion or projectile path compared to the symmetrical one. And so that's all for projectile motion. Thank you very much for watching.